Yeah, so clustering techniques usually force every instance to be assigned a cluster, which is, and so there are no outliers in the sense, no specific outliers. If you have a point that is an outlier, like for example, the point number 9 that we saw before, it was kind of an outlier. It was standing out of the other two clusters. It's very far from all other points. But if you force this to be assigned a cluster, it has to be in a cluster. Every point has to be in a cluster. Then it will be included in the clustering method, and it will somehow be, fit into that. But that can be dangerous. That can be bad for the clustering process, because maybe like one outlier or a few outliers completely screw up the whole process, and you end up with meaningless clusters simply because you could not remove the outliers, and then you have distorted results. And it's also true that clusters are usually not very robust. So different subsets of the same data set will yield different clusters. If you break your data set down into subsets and you apply clustering, probably you will get different results, which kind of tells you that the clusters that you're detecting could be a little bit forced. They're not really natural clusters, so to speak, but they're forced to be there because the clustering may not be very robust. This technique that I'm going to show you now, DBSCAN, is a much more recent. It's a much more. It's not actually not that recent anymore, because things evolve fast. But it's still nowadays heavily used, if not in slightly improved versions. That's always the case with machine learning, right? The moment you publish a successful method, then it starts to be improved by other people, like almost immediately. So in its raw form, it may not be super used, but in improved forms, it's very heavily used. So it's a much more modern, let's say, so to speak, perspective on clustering, which is called density-based clustering. So it's not anymore about just like partitioning the data points, but it's about density. Clusters should be dense areas of points, right? Not and outliers. If you have outliers, they're just like scattered around everywhere, then it's okay to just not have them in the clustering at all. DBSCAN introduces that idea that you can actually just ignore outliers, and the results are very good. So points close together will belong to the same cluster. This is a little bit like aggregation clustering. And isolated points will be left out of the clustering. So differently than the aggregation one, you can actually decide to ignore outliers and not even consider them in the clustering at all. So that's actually quite interesting. So we start with this definition of an epsilon neighborhood of element X. So if you have any element X, then you have a neighborhood. I'm just going to say neighborhood for short, but you have a neighborhood of that element, and that neighborhood is all other elements whose distance to X is smaller or equal to epsilon, which is, let's say, like a radius. You can think of it as a radius, right? So everything that's inside that radius is considered to be the neighborhood of that point, and every point has its own neighborhood, right? Some of them share big parts of their neighborhoods, but each point has their own neighborhood, unless they're exactly the same. So they have the exactly same neighborhood, but usually not. So in this example here, for example, you have point Q and point P. They both have their own neighborhoods. This point over here is shared between the two neighborhoods. They are in each other's neighborhoods. So Q is in P's neighborhoods and P is in Q's neighborhoods. But this point over here, it's not named, but this point over here is not in Q's neighborhood, only in P's neighborhood, because it's over here and it's, so simple enough. So let's take a look at the algorithm now. Find the neighborhood of every element of the data set. Basically, that's what this is just a simple, again, artificial example. The green circles here are the neighborhoods of every element of the data set. You can see that some of them are sharing some points, some of them are not. Then assign, I don't know what was that noise. Okay. Assign all elements that share a neighborhood to the same cluster. Now, this is what we get if you assign all points, all elements that share a neighborhood to the same cluster. Let's see if I have, well, yeah, maybe I should have the circles over here. So anyway, take a point. If that point has other points in their neighborhood, put them in the same cluster. Then take those points, put the points in the other neighborhood also in the same cluster, and so on. It's like a, I don't want to say that, but it's like a spreading of a disease. So one point spreads to the neighborhood, the other point also spreads to the same neighborhood, and so on and so forth. And then you will find these neighborhoods like this yellow, blue, green, and purple here, because they kind of like spread out. The neighborhoods spread out from one point to the other and to the other and to the other and so on. And as you can see, this guy here, is in its own cluster. It's blue because there was no one else in its neighborhood. And then these two guys are in the same neighborhood, and these five guys are also in the same neighborhood. So then you get these four clusters because of these neighborhood sharing, so to speak. The next step is to find the elements who have less than minimum points in their neighborhood. These are candidates for being considered as noise or outliers, right? And in this case, I have defined minimum as being 2. This is a parameter. You define it. You can define it as 3, 4, 5. It's hard to say exactly what is a good number. It depends on the data set. But I've defined it as being 2. So what I want is, okay, I want to find all the points who have less than 2 points in their own neighborhoods. So for example, this guy here has less than this guy here has less than 2 points, just 1. This guy also has less than 2 points, it's just 1, and so on and so forth. Both of them also have less than 2 because each one just have 1 point in their neighborhood. So these are candidates for noise, okay? But they're not considered as noise yet, because if they are in the neighborhood of a core element, and in this case, core is a point that's not a candidate for being noise. So for example, in this case, these are core, the yellow ones are core, the purple ones are core, because they're not candidates for outliers. So if these core elements have one of these candidates in their neighborhoods, so these are not outliers. So let's say that the core guys, they reach out and bring these candidates of outliers back in the cluster. And finally, those who were not brought up to the inside of the cluster by the core elements, they are actually considered as being noise or outliers. Let's call them noise. And they are not part of any cluster. They're just gray or something. They're just like, this is noise. Forget about these guys. They're just getting in the way of the clustering. And finally, we ended up with 2 clusters. And as you can see, we never determined how many clusters we wanted to have, right? It just ended up having 2, but like, yeah, okay, so this is a little bit easier to see. But anyway, we never determined that we wanted 2 clusters. However, we did determine the minimum, the min, and we also determined the radius. So there are 2 parameters, the radius that each point will include the neighborhood, and the minimum number of points in the neighborhood for a point not to be considered as noise. But the number of clusters themselves, they just came naturally from the data set, okay? Which is quite interesting. It's different than what we had in the previous one, where we just computed every clustering and then we chose whatever we wanted. In this case, we don't choose anything. We don't choose the number of clusters. We choose the parameters, and the number of clusters just comes naturally. And this is a very interesting example that you can absolutely not do this with k-means. K-means would never work with this because of this intertwined clusters, like one where they kind of branch into each other. So you could never have correct definitions here with k-means. K-means would just draw a line between them and separate them somehow. So this is the original data set. Again, for us human beings, it's easy to see the clusters, right? You can see there's this U here, then there's another U upside down here. There's like an upside down T and so on, a curved cluster over here. For us human beings, we can see that. For the computer is much harder. This is the results after, these are the results after doing this first pass, where you get the core elements, you get the border elements, which are candidates for noise, and you have the actual noise elements, which are not included in any cluster. And finally, we actually have the clusters here, each in a different color. So this U here is a cluster, this is a cluster, and so on and so forth. Now, again, this is because the parameter settings here were very clearly defined in a way that worked, right? It may not be that super obvious like that. Again, we're gonna go for a simulation here because I want to show you. I think it's really interesting. And again, I really need to know if you can see the web browser. Do you see the web browser? Yeah, okay, thank you. So then we can choose here, what kind of data would you like? Anything. I can let's say like smiley face. Yeah, like a smiley face. Don't worry about these circles that are spread around. Just think about the actual data points here. The data points form a smiley face. So you have the outline of the face, the two eyes, and the mouth, right? So this is supposed to be 4 clusters. Again, the whole outline of the face, each eye is in a cluster, and a mouth should be also a cluster. It's randomly, so maybe the mouth will be broken down here into 2 clusters because some points were, let's see. The epsilon here is the radius. Right now it's defined as being 1, and the minimum points is 4. Let's see how it goes. So go. And then you can see that it starts spreading randomly. Okay, so the algorithm here just started from a random point and started spreading. And it will go on spreading until it cannot do that anymore. So again, in this case, it's just take a point, take the neighborhood, assign all those points to the same cluster, then jump to these points that are in the neighborhood of that random point, assign the same cluster to all the neighborhood points, and so on and so forth, and just keep going until there's no one else. And then when it's over, it jumped randomly to another point that didn't have a cluster yet, and just assigned that. And as I predicted, the mouth here was broken down into 2 different clusters because randomly a subset of points was, just randomly spread, a little bit spread out of the mouth. So that's not perfect. So we're going to try something else here now. But anyway, it was a good result, right? And I think it was you could see clearly how the algorithm works here. It basically just start from a random point, spread to the neighborhood, take those neighbors that were assigned, spread it again, and so on and so forth until you can't reach anyone else. Jump to the next random point that was not assigned to any cluster yet, and start doing the same process over and over again. And this was the result. But of course, I'm not. Yeah. Unfortunately, I wanted to actually change the parameters, but for some reason I couldn't. Yeah. And anyway, we could do this. I'll try something else more interesting. Well, for Gaussian circles like this, it always works. A pimpled smiley face. It's a smiley face with more noise, right? Because the problem was in the previous one, we didn't have any noise. We didn't have any points that were classified as noise. Every point was in a cluster. And I wanted to show you how it works when some points are actually considered as being noise. So this is like the pimpled smiley face because it's still a smiley face, but it has more like randomly, spread out points that are probably noise, basically. Let's see what will be the results. I wish I could accelerate this a little bit. Yeah. So, okay, it's over. Jump to the next random point. Now it's the mouth. Yeah. So as you can see, now it keeps jumping around. Yeah, so now it covered every point. And as you could see, it kept jumping around between some of the noise points and trying to see if they would fit into any cluster, but they couldn't fit into any cluster. So they were just left out as noise. And again, we had this little cluster over here because it just happens to be like that. So yeah, so this is DBSCAN. I'm gonna go back to the slides. I hope that was more or less Okay, so you're seeing the slides now again. Okay, all right. The slide, actually, not the slides, but the single slide. You see it. Okay, thank you, Camila. So hyperparameters, two hyperparameters, the radius and the minimum. And again, how to pick their values? Hard to say. Try and error, or the elbow method again. And again, you can, for example, fixate minimum, and then compute the distance from every point to their neighborhood, their minth neighborhood. And then you can see here that when you got an elbow over here, that's could be a possible value for the epsilon. So it's a possible good value for the radius, because it's the point, it's the, let's say, the average distance from points to their minimum minth neighbor. So they're the farthest neighbor that they can actually reach for. And then that's a possible good value for epsilon. I don't know. You know, before you actually do the clustering at all, you just take every point, compute their distance to the, for example, if minimum is 4, then for every point, compute their distance to their fourth neighbor, and then at some point you will see that the elbow goes up because the cost just shoots up, and you don't want that. So then, yeah, something like that. That's one possibility. The strengths of DBSCAN is that it's robust to noise, right? And also finds clusters of different shapes and sizes, which doesn't happen with k-means, for example. It does happen up to a certain extent with the hierarchical clustering, but for sure not with k-means. So you can get like this is a cluster, this thing is a cluster, and then this big one here is a cluster. And then if you, as you can see here, if you change the epsilon value just a little bit, if you go from 9.92 to 9.75, then basically everyone else becomes noise, and only these points in the middle over here, these are the only ones that become considered as mean clusters. So as you can see, it's very sensitive to parameters. You change just a little bit from 9.92 to 9.75, and then all of a sudden you're completely disregarding your entire data set and just considering these, because it cannot adapt to varying densities. This is the important part here. When clusters have similar densities between themselves, then they can be considered as clusters. But since these clusters over here, they have very high density, and the rest of them not, they're very low density, and even especially this one here is very, very low density, then DBSCAN cannot deal with that. It cannot understand that different clusters have different densities, simply because the epsilon value here is fixed, right? Okay, so then that was like the most important part of the lecture, and we are almost at the end. So we have like actually 7 minutes to 12. Now, as always, there is extra content that I always prepare extra content in case we have more time, or in case some of you guys wanna go on. But the most important part of the lecture was this. And actually, I'm gonna jump some of these things to the end, just so I can show you something else that I wanted. Oops, that was too much. I wanted to show you this as one final picture for the main part, let's say, of the lecture, which is a comparison between many different clustering techniques, right? This comes from scikit-learn. These are all the clustering methods that are implemented in scikit-learn, and they're all tested with these 6 artificial data sets. And it's very interesting to see how the different clustering methods will behave with different data sets. So the ones that we have seen in this lecture were k-means, which is called mini batch k-means in scikit-learn. So it's the first one here. Actually, I'm going to mark this here. K-means. We also saw the agglomerative clustering, and we also saw DBSCAN, right? So these were the 3 ones that we actually saw in the lecture today. And as you can see, there are lots of other ones. So let's take a look at some things. Like, for example, first of all, yeah. So first of all, so this one, and this one. First of all, if you look at this row over here, everyone basically just does the same, right? Every clustering method works exactly the same with Gaussian clusters like this. This is the easiest possible challenge for a clustering algorithm. And every clustering algorithm will basically work the same with this. So if you have a clustering algorithm that does not work the same with this data set, then probably it's a very bad one. So you should really, really look like, well, what's happening? Because this is basically like challenge number one for clustering solved, okay? And then, as you can see, there are some other challenges that involve different things. Like, for example, constant rings with the same, one within the other, concentric or concentrical, I think. I don't remember now. But basically, data points that are one within the other. K-means completely, it cannot do that. K-means just cannot do that because K-means always has to separate the points with like lines or hyperplanes, let's say, if you're in a high dimension space. It has to draw some kind of a hyperplane and then divide the points with that. So it's impossible to do this. Well, in its original, in its original formulation, it's impossible to deal with data clusters that are one within the other, okay? So fail here fails with this one because of the curved aspects here. With this one, well, if you ask for 3 clusters and there aren't clusters, then I guess everything will fail. Not everything, because maybe mean shift, but most of them will fail. So because there's just no clustering here, and you asked for clusters, so k-means is kind of like, okay, I'm giving you clusters, but I have no idea if that makes sense. And as you can see here, this is kind of like an extension of this one. These longish clusters, and k-means also fails horribly with that. With this one, which are 3 clusters with varying densities and varying sizes, k-means fails, but not horribly. You see, you can see here that only the points from the middle cluster kind of gets wrong. Some of them here get wrongly assigned to the orange clusters. It's a failure, but it's not a horrible failure. But anyway, you can see from these results how k-means is very, very simple, right? Then agglomerative clustering can deal with things that are one within the other, and can also deal with this things over here, like for example this one. It also works very nicely with this one, surprisingly, right? Because this is a little bit of a harder problem, and agglomerative clustering still works very nicely. Fails with this one for whatever reason, who knows. And kind of gives a good result for this one also, which is, again, like, okay, you want 3 clusters, here are 3 clusters, but you don't even see the green one is just a couple of points over here. The orange ones are just a couple of points over here, but most of them are just blue. So most of this is 1 cluster, but since you want 3 clusters, take these 2 smaller ones, which it looks like a good result. DBSCAN also works very nicely for these data sets one within the other, again, because of the whole algorithm that we've seen before. Then it also works very nicely for this ones, again, because of the spreading, of the disease, so to speak. It starts spreading and goes until it cannot stop anymore, and then jumps to the next one. So it works nicely. Fails for this one horribly. Don't ask me why. It finds just 2 clusters and puts these 2 together. I guess it's because they have a connection over here. So, the clustering starts spreading, just keeps on spreading through this like bridge. Kind of works very nicely for this one though. Actually, probably the best one other than Gaussian mixture. Works quite nice with this one. And also gives quite a nice result for this one. And I guess it's along with mean shift is one of the best results, because basically in this case it just said, look, there's just 1 cluster here, period. And DBSCAN can't do that, because with DBSCAN you don't really define the number of clusters, right?